Hi, my name is Walker Gallman. This is my lab report video for Lab 2 Charge Tapes Revisited. The purpose of this lab is to compare the electric force from the point charge model of the floating tape in Lab 1 to a line of charges. Additionally, GlowScript was used to create a computational model to simulate the tape and interacting forces. The main results from the lab include that the estimated point charge, which was gathered in Lab 1, was 1.074 times 10 to the negative 8th coulombs, and the line of charges has a charge of 2.268 times 10 to the negative 8th coulombs. Three fundamental physics principles were used in this lab. The first is Newton's second law, which is a principle that states that the net force on a system is equal to the change in momentum over the change in time. The gravitational force, which is an equation used to find the gravitational force between two objects, in this application between the piece of tape and the Earth. And the third and final fundamental principle is Coulomb's law, which describes the force of attraction or repulsion between electrically charged objects. Coulomb's law is a principle that is used to find the electric force between two charged particles with charges q1 and q2. Since we are comparing the line of charges model to the point charge model from Lab 1, let's recall the main results from Lab 1. The floating top tape was treated as a point charge and its charge was calculated accordingly, and the bottom tape was considered part of the surroundings, exerting an electric force on the top tape. In this lab, we take the same approach but divide the bottom tape into smaller charge segments, treating it as a rod of point charges rather than a single point charge. We follow the same three major steps as in Lab 1, such as finding the gravitational force acting on the floating tape, and we set that equal to the electric force, and since the tape remains stationary, that means the forces are balanced and they are equal in magnitude but opposite in direction. And the third and final step was to use the electric field of a rod to solve for the charge on the floating tape. Since we divide the tape into many tiny charge segments, it behaves like a continuous line of charge, making the electric field of a rod a more precise model. And here's the derivation from the formula of the electric field of a rod to find the charge. And as we found earlier, the charge was equal to 2.268 times 10 to the negative 8th coulombs. A GlowScript simulation replicated the experimental process accurately modeling the electric field, gravitational, and electric forces. To implement this model, we first needed to define constants and initial values, and also two functions were used, one to generate the electric field, and the other used to create the line of charges through iterations in for loops. The bottom tape is split into 50 segments, each acting as a point charge, and a for loop was used to iterate over these segments. For superposition, the superposition principle was used, where each segment contributes to the total electric field, which we sum up using nested for loops in the computational model. This model produced a graphical representation showing 50 green arrows representing the electric field from the bottom tape, the top tape in red interacting with the field, and the electric and gravitational forces, which were nearly equal, confirming force equilibrium. As with any model, we made assumptions to simplify calculations. For these assumptions, we neglected air resistance and friction, assumed uniform charge distribution on the tape, and assumed each piece of tape carried the same charge. Potential sources of error include measurement inaccuracies during the data collection period, or charge loss due to handling and environmental factors. Moving on to the discussion, the point charge versus line model provided two different answers. The point charge model said that the charge was 1.074 times 10 to the negative 8th coulombs, and the line charge model is the 2.268 times 10 to the negative 8th coulombs. And as for why do these models differ and which is closer, this was the approach in Lab 1, but Lab 2 showed that this overgeneralized the charge distribution. The line of charges model is likely more accurate because it accounts for small charge segments along the tape's path rather than assuming all charge is concentrated at a single point. The difference in charge values between the two models arises from different levels of precision, with the line charge model offering a more realistic estimate.